So we want to look at the equilibrium constant, which is given the pronumeral K, capital K. And what we are measuring here is the position of the fulcrum, if you like. If we think about our reactants on this end and our products here, the equilibrium constant, K, tells us which side is favoured, if you like. So, is my balance point there for this particular temperature? Okay, so our equilibrium constant is only for a specific temperature. We are able to move that position for K if we change the temperature. That is the only way we can change the position. And that's a really important point, because when we go changing the some concentrations, etc., that is going to impact on the concentrations, but it doesn't change K. Okay, so that where that balance point is remains the same. Now, how do we therefore work out what K is? If we think about a generic reaction, and this is on your formula sheets. And so we're saying that P and Q are our reactants. And X and Y are the coefficients for our balanced equation. Same over here. These are still our coefficients. And in this case, though, R and S are our products. So that's how you read that information, and it's present, well, I know it's present in the next format. And so what we can say is that at equilibrium, and that would be an acceptable abbreviation of equilibrium, or you can write something like that. At a specific temperature, remember that's really important, that K then is equal to the concentration, and what we're going to use now is this shorthand of square brackets representing concentration. So our concentration of our products, and they are multiplied, divided by the concentrations of our reactants. So we have R and S and P and Q, and they are to the power of the coefficients. So here we've got R to the power of Z, and S to the power of W, P to the power of X, and Q to the power of Y. Now, there are some reactions, if you like, where we ignore things, and we ignore solids. We can't have a concentration of a solid. We also ignore it if we have water and it is the solvent. So if I have a reaction that's producing water, but it is in aqueous solution, then I don't include the water in my calculation for K. Okay, let's think about that. So just say it was an acid carbonate reaction in solution. Then we know that one of the products of that would be water, but because it's in solution, we would ignore it. If it is as a gas, if the water is as a gas, as in steam, then we do need to include it in our calculations. If it is a product and it's not in aqueous solution, we would need to include the water. Okay, so we are ignoring water. For aqueous reactions. As a reactant or a product, doesn't matter if it's in aqueous solution there, but we count it for a gas and as a product or reactant is not aqueous. So for example, we know that we can form an alcohol if we react an alkene with steam. In that case, we would need to include the water. So, when we say we're ignoring it, we can't assign it a value of 0. If I put a 0 here, what's going to happen to my calculation? It would just be 0 at best or undefined, depending on where the 0 was, wouldn't it? So what we do, if we're ignoring it, it's assigned the value of 1. That way it makes no impact on the calculation, but the calculation can still proceed. So when I'm saying here we're ignoring, it's assigned the value of 1. And as I said before, it's the same for solids. Because we can't really calculate the concentration of a solid, can we? What is it? What would that be? And so it is assigned a value of 1. They don't change with in the context of this. It's our reactants that are going to be changing. So point 2 here also tells us that K is large. K is considered large if it's greater than 10 to the 4 and small if it's less than 10 to the minus 4. But we can say that anything greater than 1 favours what? Any value greater than 1 favours what? How many people are doing maths specialised? I'm asking you to tell me whether we've got here, what have we got up here? We've got our products on the top and we've got our reactants on the bottom. So if they were the same, then it would be 1. That would mean that equilibrium was basically balanced right in the middle. But I'm asking you, which way is favoured if the number's greater than 1? Products. And so therefore, any K value less than 1 favours reactants. So if we have a large value, that's telling us that the equilibrium favours the forward reaction. Okay, so this is a large K, and then this would be a small K. Does that make sense? It's telling us which way or which side dominates at equilibrium at that particular temperature for that particular reaction. But sometimes students get a bit tangled up or a bit worried about these numbers because well, what happens if it's 10 to the 3? Is it still large? Well, it still favours the products. And so we have this reaction, a relationship between the forward and reverse reaction that basically it's the inverse. So K reverse, K of the reverse reaction is equal to 1 over K of the forward reaction. Okay, so i.e. inverse. And hopefully that should make sense, because what are we really saying? If I rub out a little bit of stuff here. What we're saying is, if we're doing the reverse reaction, then we've got R, ZR, and WS on the reactant side, haven't we? That way, and then we've got XP and YQ are the products. And so if I'm calculating K of the reverse reaction, then it's going to be still these ones on top, P X plus Y. Does that make sense? R to the Z. Oops, it's not plus. T. Okay, so that's why it's the inverse, isn't it? Because we've had to swap them over. What was on the bottom has ended up on the top and vice versa. So that is why that is the relationship between K for the forward and the reverse reactions. All we're simply doing is putting them on, putting them around the other way. Now, an important point for point 4, K changes with temperature, and it won't necessarily favour the production of the products. What it does is it depends on whether it's an exothermic or endothermic reaction. So for an endothermic reaction, K increases as the temperature increases. And for an exothermic reaction, K decreases as the temperature increases. So I'm going to rub, you right if I rub this out? Yeah, I'll fill it anyway. Just back at it. So let's have a look at why that's the case for K. Let me just, I don't know, I'm going to burn some magnesium, say, because that's a fun thing to do. No, that's not going to be a good thing, is it? Because I really need an equilibrium reaction, and that's not going to be an equilibrium reaction. Alright, here we go. 2NO2 and 2O4. Delta H is negative. Now, this is an equilibrium reaction, and so the way we have to read this is if the reaction proceeds left to right the way we normally read in English, so reading this way is exothermic. Because it is an equilibrium reaction, I could easily write it round the other way, and that would be endothermic, wouldn't it? So I could say N2O4 to NO2, delta H must be positive, because this time when I read it from left to right, it's endothermic, the opposite. Does that make sense? Okay. Now we know from right back at the beginning when we looked at thermochemistry that we could also think about writing down our energy as either a reactant or a product. And so for an exothermic reaction, we are releasing heat. And for our endothermic reaction, we're going to need to add heat as a reactant, if we're thinking of it in those terms. And so, what does K do then? If I'm adding more heat to an endothermic reaction, then I'm going to be increasing the concentration, if you like, of a reactant. And what happens is the system adjusts to minimize that change, which we'll get to Le Chatelier's principle later. But what that does is it therefore favors the forward reaction. Okay, and so therefore, because this is the product, K will increase. Okay, were you able to follow that logic? We increase the concentration of a reactant, and so that drives the forward reaction. Because that's led to an increase in the production of products, K has increased. Now, because here we are releasing heat, and so if we add heat to this system, then we're going to be driving the reverse reaction, because, again, when we think about Le Chatelier's principle, we'll see why that happens. And so that means that K will decrease. And of course, we've increased the concentration of our reactants rather than our products. Now, there are lots of subscripts we can use. So you often see that one for concentration, and so we can use that one for gases as well as for in solution. But there's another one that's an important one, and that's KSP, and this is the solubility product. That's what the SP stands for. And this tells us about how readily a compound will dissolve. So if we have a very high solubility product, then, so if this is large, then it will precipitate. Because that's really telling us that our just let me check that. I think what I've said there is incorrect. I don't want to say the wrong thing. Small solubility product will be for the larger the concentration of the ions, small means insoluble. Yeah, it did make sense. Because when we say things are soluble or insoluble, we've already thought about things being on a continuum. So some things are very soluble and some things are very insoluble. But if we put anything in water, so if we could drop a gold ring into deionized water, and some of the metal atoms will be released from the gold ring into the water.